Hello everybody, welcome to our project of a two-player digital dice game. This is the digital version of the traditional throw the dice game. The rules are pretty simple. There are two players, each of them has a scorecard. There's a game switch in the playing board. When a player presses that switch, he scores a random point that is displayed in a digital dice face constructed with LEDs. This point is added to his score in his scorecard. The players take turns to score their individual points, and at any period of the game they can check the scoreboard to assess who's leading or, in the end, who wins. Now let's take a look at the operating circuit of the game. The operating circuit has four parts. Firstly, we have the random number generator that generates the random point scored by a player when he presses the game switch. This part of the circuit consists of three major ICs: a 555 timer, a 74161 synchronous 4-bit binary counter, and a 74195 parallel access shift register. The 555 timer is operated in astable mode to generate frequent pulses of logic high and logic low. The frequency is determined by the value of these two capacitors and these two resistors. In our game, we have set the frequency to a considerably high value to make the random number generation efficient. The pulses generated by 555 timer are fed to the 161 synchronous counter, which in this case counts upwards at each rising clock edge. We have set the preset value of this binary counter to 0001 binary to make it start the count from 1. We've also added a feedback from the output via a NAND gate and to the load pin here, so that the counter restarts its counting once it reaches 6. As the counter continues to count from 1 to 6 at a very high frequency, its output is fed to the 195 register. We have set logic low to pin 9 to make the register work in parallel mode. Pin 10 is the clock pin, which is connected to the game switch through a debound circuit. The debound circuit we used is constructed with a 555 timer and some resistors and capacitors of appropriate values. As a player presses the game switch, the register gets a clock pulse and momentarily transfers its input bit pattern to its output pins and stores it there. Thus, we get our random number point at the press of the game switch. Since the counter only counts from 1 to 6, there is no possibility of getting a random number higher than 6 at the register output. So, for the next part of the project, we can ignore the most significant bit of the register output and deal only with the last 3 significant bits. Now we move on to the next part, which is digital dice face. This part is actually pretty simple. We just took the output from the 195 register, processed it with a small logic circuit, and displayed the random number in a dice face fashion with 7 LEDs. The next part is the adder binary to BCD converter part. This is the largest and most complicated part of the circuit. The understanding of this circuit is rather long and theoretical approach which can be found in the digital logic design textbooks. In this context, however, we can focus on what this part actually does. What it does is, it stores the binary coded decimal representation of the current score of a player, and when the game switch is pressed and a new number comes in from the random number generator, it adds that number to the current score of the player to give a new score. Then the score is displayed in 7-segment displays. The adder circuit of our game is capable of adding up to decimal 999, and to do this we required 6 7483 4-bit binary adders, 3 74195 parallel access shift registers, 6 AND gates, and 3 OR gates. In our game we needed 2 of such adder-cum-BCD converter circuits for the 2 players. Now, as there are 2 players in the game but only one random number generating circuit, the obvious question is, when the game switch is pressed, how does the circuit decide which player gets the new point? To control this, we have placed another part before the adder circuit. This part again is divided into 2 segments, each with 3 AND gates. Let's call them segment 1 and segment 2. In each segment, 3 of the 6 inputs of these 3 AND gates are taken from the 195 register of the random number generator. In segment 1, rest of the 3 inputs come from a 74112 JK flip-flop, which halves the game switch clock frequency. In segment 2, These rest of the 3 inputs come from the same JK flip-flop IC, but via a NOT gate. This mechanism ensures that only one of the 2 players gets the generated random number as his point and the other player doesn't. It also ensures that any 2 consequent random numbers are added to each of the 2 players and not to the same player. This extra NOT gate just after the debounce circuit of the game switch and before the adder circuit is very tricky. Without this gate, the circuit should work just fine in simulation, but it's extremely important in real-time implementation of the circuit, and without it, no adding will be done in reality. To understand this fact, we have to focus on the fact that the debounce circuit output is not only connected to the random number generator but also to the 195 registers of the adder circuits. So when the game switch is pressed, not only a random number is generated, but also in that same rising clock edge, the adding operation is done. But the ICs in the random number generator causes some time delay that makes it impossible for the adder part to work properly, because it will get the clock pulse input before it gets the random number input. But when we add a NOT gate before the adder circuit, the clock edges for the adder part is inversed. That is, when the game switch is pressed and the random number generator gets a positive clock pulse and generates a random number, the adder circuit gets a negative clock pulse, so it holds the adding. Then when the game switch is released, the adder gets the positive clock pulse and adds the random number which is already present at its input. Lastly, we have a reset switch that is connected to the reset pins of all the 74195 registers. So as the switch is pressed, the whole game returns to its initial state. Thus the total operating circuit of our little game is complete. So let's now press the switch and let the game begin. Push random number 4 and add it to the player 1. Second push random number 2 added to player 2. Third push random number 3 added to player 1 and with his previous score added, and now the score is 7. Again 1 added to player 2. Again 3 added to player 1. Again 4 added to player 2. Now 6 added to player 1. Then again 6 added to player 2. The game is very close now. Now the last switch push and player 1 scores 4, so it's a clear win for player 1 no matter what comes out now for player 2, but still he gets only 2. So now player 1 is the winner and player 2 is lagging by 5. Now we are going to reset the game. This is the reset switch. If we push the switch, both scores are reset and random number is 0.